Okay, so our first question, we have a cylindrical wire frame for a wastebasket. Has a wire circle for the top and the bottom and 6 straight wire rods that hold the top and bottom circles together. The total amount of wire used is 4 meters. That's going to be important for us in solving this question. What radius and height will maximize the volume? That's important. We need to know what exactly we're trying to maximize or minimize of the cylindrical frame, and then round your answers. Okay, so 2 very important pieces of information here. What we want to maximize, or in some problems minimize, and it's telling us a certain condition we have. Okay, so let's start with the condition. We have a total amount of 4 meters to use for wire. So I'm going to say the length of the wire that we have is 4 meters. Okay. And what wires are we using here? So we have 6 vertical wires and 2 circular wires. That means this 4 meters is going to comprise the 2 circles. So the 2 circles. And that'll be the circumference of a circle, which is 2 pi r. So we have 2 of these. And the 6 vertical wires. And that's just going to be their height. And that equals 4. All right. Next thing is they want us to maximize the volume. So let's write volume. Now this is a cylinder. So the volume of a cylinder is just the area of the base, which will be pi r squared, times the height, h. Now it says we want to maximize the volume. So it's the volume that we want to take the derivative of. But in this case, with respect to what? R or H? Well, you should only have one variable, right? And what we're going to do is do it with respect to R. I think that would be easier. And so what I can do then is take this equation here, solve for H, and substitute that back into volume. If I do that, I will have a function for volume which is only on R. And then I can find the derivative. So let's start there. So we're just going to rearrange this equation here. So I can start by just taking 4. I'm not going to write m, because I find when I do that, a lot of people think m is some sort of variable. That's just the units, 4 meters. So I'm just going to leave it as 4. And then I'm going to subtract 2 times by 2 pi r, which is 4, but whatever, I'll just leave it for now. And that's going to equal 6. H. Divide both sides by 6. And we get H equal to, so 4 over 6, so that's 2/3. Minus, again, 2 times 2 is 4, so 4 over 6 is, again, 2/3 pi r. Alright, so now that I have H with respect to R, I can substitute that back into our volume. So we have pi r squared times by H, which is going to be 2/3 minus 2/3 pi r. So now I have volume as a function of R. I'm going to have to take the derivative of that, but it's going to be easier if I sort of multiply through first. So let's distribute the pi r squared in. So we'll end up with 2/3 pi r squared minus 2/3 pi squared r cubed. Okay, now I can find the derivative. Alright, so this is just our power rule. So this is going to give us 4/3 pi r. And then we're going to minus, so bring the 3 out in front. It'll cancel with the denominator, so I'm just left with a 2 pi squared r squared. Alright, so now because we want to minimize or find the value of the horizontal tangent, we can set it equal to 0. And we can solve for r. So what I'm going to do is sort of factor out an r here. So we can have, I can also factor out at least a 2 pi. So 2 pi r times by, and so here we're going to be left with 2/3 minus pi r, which equals 0. So we have a couple options. One, r could be 0. That's not a very interesting option because if r is 0, we don't have a volume, which would obviously be a minimum point. We don't care about the minimum point. We care about the maximum point. So there's another solution here, and that is 2/3 would equal pi r, or 2/3 pi will equal r. So that is possibly a maxima or a minima. We would have to test that. We'd also need to look at the domain of the function. Right? What would r need to be between? Obviously it's between 0, because that's would be definitely be a minimum. You'd get a volume of 0 if r was 0. So 0 is less than r, which is less than what? That may be a little bit tricky to try and figure out what it must be less than. But if we look at h, we can do h a lot easier. Right? Now h obviously must be greater than 0. Right? But if these lengths, all 6 lengths, took up the maximum amount of wire, which is 4 meters, then each length would need to be 2/3 of a meter. Right? And then they would add to 6, and that gives you a volume of 0. So what we can simply do is substitute 2/3 into our equation for h. So if we substitute 2/3 into this equation, we get r is 0. And if we substitute 0 in for h, then we get 2/3 equals 2/3 pi r. So let me just do this over here. If we substitute h as 0, we get 2/3 equals 2/3 pi r. Or r equals 1/pi. So there's your other range. But again, these ranges we're not necessarily interested in because they both give us a volume of 0. So what about this one? If we were to figure out what the volume is when r is 2/3 pi, well, we can substitute that back into our equation for volume. So that would be 2/3 pi times 2/3 pi squared minus 2/3 pi squared times by 2/3 pi to the power of 3. Okay, so that gives us 0.031 meters cubed. Now it said it wanted to know the radius and the height. So the radius is going to be 2/3 pi. That's going to give us a maxima. And then we can find out the height by plugging r in for height. And we get height equals 2/3 minus 2/3 pi times r, which is 2/3 pi. And so our pi's cancel. And we get 2/3 minus 4/9, which is 2/9 meters. Okay? So for the second question on our quiz, it says we have a unique package, definitely a unique package, made up of a cube and a cylinder on top. The diameter of the cylinder is equal to the lengths of the cube. So what does that mean? That means if we label this cube to have length, width, and height of x, it means the diameter would be x. Or, if you like, you can set the radius equal to 1/2 the diameter, or 1/2 x. It says the total volume is 20 centimeters cubed. We're going to use that information because that's a condition for this one. What dimensions will minimize the surface area? All right, minimize the surface area. That's what you're always looking for. What you want to minimize and maximize, and some sort of condition. Okay, and then round your answers. All right, so let's start with the total volume. So the volume, well, we have a cube, right? Length times width times height, so that's just x cubed. Then we also have this cylinder on top. And the volume of the cylinder is just the area of the base, which is pi r squared, times the height of that cylinder, which is h. Now r, I've already said, is 1/2 of x. So I can immediately write r as just 1/2 x squared times by h. Okay, so that's our volume. Now it's asking us to minimize the surface area. So let's get an equation for surface area. So the surface area, well, we have 5 surfaces of the cube plus a partial one of the 6th one. So for now, what I'm going to do is sort of take all 6 surfaces. So we have 6x squared, but I'm going to subtract the area of the bottom of that circle. So we have that full square minus the area on the bottom. So that gives us this remaining portion here. So let's subtract 1 pi r squared. But then, this is where things get better though, I need to add the area of the top of the circle, so plus pi r squared. So that's nice, because those are just going to cancel. What started off seeming like, oh my goodness, turned out to be quite nice. And then we're just left with the surface area around the cylinder, which you can imagine if you sort of take that and stretch it out into sort of a rectangle. What you have is the height, and this would be the circumference. So the surface area of that is just multiply those two like a rectangle. So plus h times by 2 pi r. Alright, now the question is asking us to minimize the surface area. So I need to take the derivative of a. But take the derivative of a with respect to what? Right? If I were to write this in Leibniz notation, it would be dA by d what? So what we're going to do is we're going to do it with x. So take the derivative of a with respect to x. But that means I have an h here and an r here. Well, an r I can easily replace with 1/2 x. Now the h we're going to get from the volume. So let's rearrange and solve for h in the volume. Now we know the volume is 20 centimeters cubed. And so that's going to equal x cubed plus pi over 4, because it's 2 squared, x squared h. We're just going to rearrange this to solve for h. So we get 20 minus x cubed equals pi over 4 x squared h. Okay, then I can multiply by 4, divide by pi, and divide by x squared. So we get 4 over pi x squared, all times by 20 minus x cubed equals h. And I'm just going to expand it because it'll be easier to take the derivative if I expand that. So we get 80 over pi x squared minus 4 x. Right? We've got an x cubed over an x squared. So we're just left with an x over pi. And that's h, so I'm going to substitute h in there. So we have 6x squared. Hold on, I'm not going to take the derivative just yet. Let's just simplify this area a little bit first. So we get 6x squared plus h, which is 80 over pi x squared minus 4x over pi, all times by, we have 2 pi times r, which is a half x. So 2 times a half is just 1, and so we're just left with pi x. Okay, so let's take that. I'm going to distribute the pi x. So we have 6x squared plus, that's 80 over x, minus, this will give us 4x squared, and the pi's will cancel. So minus 4x squared. So now I can find dA by dx, which gives us 12. 2 times 6 is 12. X plus 80 over x. That you can consider that x as x to the negative 1, so that's going to be negative 80 now. So negative 80 times x to the negative 2, or over x squared, and then minus 8x. Alright, and to find where that's going to be a minimum, I'm going to set it equal to 0. And we're going to solve. So, to help with solving this, I'm going to have 12. Let's multiply each term that doesn't have an x squared with x squared over x squared. So I'm going to have 12x cubed over x squared. And they're all going to be over x squared. So minus, this one we can leave as 80 over x squared. And then minus 8x cubed all over x squared equals 0. So since it's all over x squared, and I know x isn't going to be 0, that's not one we care about. In your domain, sure, x will be 0. In fact, you can think of it as 0, x being between 0, because if x was 0, that essentially just reduces everything to 0. You don't have a volume at that point. So that's definitely minimizing, but way too much. Right? And it's also going to be less than, well, if we only had the cube, then the, if it's 20 cubed, you can think of that as the cubic root of 20. So since I want to know when this is 0, I can just look at the numerator. Right? We have 12x cubed minus 8x cubed, so that just gives us 4x cubed minus 80 equals 0, but I can bring 80 to the other side. Okay, divide by 4. Running out of room, so I'm just going to move over here. So we have x cubed equals 20. That should be a cubed. And therefore x equals approximately 2.71 meters. Right? So now that you know what x is, you can also figure out what h is, because you have an equation for h. So substitute in your x value, and you'll get h as 80 over pi times 2.71 squared. I believe it's 0.017. So those are your dimensions in order to minimize the surface area of your package.